Hey guys, welcome back to the Beginner's Guide to Restoring Early Tube-Based Black and White Televisions. In the last installment, we did some work topside, including testing tubes and working inside the high voltage cage. I thought in this installment we'd start out by talking a bit more about what's actually going on inside that enclosed box, namely horizontal deflection and high voltage generation. It's a complicated topic. The techniques evolved a lot in the pre-war days, and by the time commercial television production launched in the US in '46, it pretty well worked out one scheme to do it that took over, and that's what this set uses. But there are other ways to do it. What am I talking about? Well, let's just take a real basic diagram here. We have a screen, and we have an electron gun that's shooting out a beam of electrodes towards that screen. We need to deflect it both vertically and horizontally. A few ways to do it. One is electrostatically, which we'll talk about in a separate series, in which case you would have some deflection plates, metal plates, two going this way, two going that way, and you would put an electrostatic charge on them, and you would repel or attract the electron beam to make it go up, down, left, right. Or you can do it magnetically, which is what this set does, in which case you have coils. Have a set of coils vertically and horizontally. And these are actually connected up in the middle, and they're driven by circuits. Well, we worked on the vertical. I didn't talk a whole lot about how the actual output goes to the yoke. So let's talk about the vertical briefly. The vertical has a beam power tube, a 6K6, that drives the primary of vertical output transformer. And the secondary just goes right to the yoke. Nothing fancy. It's just like driving a speaker. They do add a couple resistors here, and it's tapped in the middle. That is, those are there to dampen any potential oscillations. So one thing that's maybe a little different than driving a speaker is that instead of having some combination of sine waves, we are doing a sawtooth where we want to push the beam across the screen or from the top to the bottom and then snap it back. So one of the challenges with doing that is if you ever worked with a magnetic field, like a relay, when you charge up an inductor, it builds up a magnetic field. When you disconnect it, that magnetic field collapses and the magnetic field lines cut across the wire, which creates power. It needs to go somewhere. That's why in relays they add a diode across the coil to give that power a path to go safely. If you don't, you get a spark. So the challenge with these TVs was, we gradually build up a charge, we push the beam across, or down, or up. When we get to the end, we want it to snap back, so we cut the power. The sawtooth goes down. We still have all this energy in the coil. Where's it going to go? Well, it's not that big an issue with the verticals. It's a much, much lower frequency. And we've got some time to go from, say, the top to the bottom and then back up to the top. Horizontal is a whole nother beast because it's a much, much higher frequency. So the vertical frequency is 60 hertz. So we're talking milliseconds. The horizontal is nearly 16 kilohertz, so we're talking microseconds. We need to snap that beam back because we're scanning very rapidly across the screen. We got to snap back in a very, very, very short amount of time to get ready for the next scan line. There's a lot of energy we need to dissipate, or I should say there's some amount of energy we need to dissipate very, very quickly. How much energy? So there's another factor. How energetic is this electron beam that's going towards the screen? That also plays into how difficult it is to deflect. If this is only, say, running on a couple kilovolts, it's a small screen, it's relatively easy to deflect, either electrostatically or magnetically. When you get larger and larger, where you're talking 10,000, 15, 20,000 volts, and a much larger screen diameter, it takes more and more and more energy in these magnetic coils to deflect that electron beam, because it's accelerating faster and faster and faster, which means you need more and more of a magnetic field to deflect it, and quickly. So that's why all that stuff in that high voltage cage, we saw the 6BG6, the big Coke bottle horizontal output tube, and big Coke bottle 5V4 damper tube. We need those beam power type tubes to generate and control this power. Okay, so in this particular set we have, let's round it up, it's around 8,000-9,000 volts, let's just call it 10 kilovolts, and we have a 12-inch screen. So as far as TVs go, that's fairly modest. You see me do a lot of predictives. They typically have a 17 or 21 screen and run on 16,000 volts. So a bit more of a challenge there. But this is earlier, so it's a little bit easier to do. Some of you commented on the fact that it uses a 5V4 damper. 5V4 isn't really a damper. A 5V4 is a half-wave rectifier tube. But back when this set came out, there really weren't any dedicated TV damper tubes on the market yet, so they double up the plates in the cathode and use a 5V4. Some sets use triodes, actually. I'll get to what the damper tube is for in a moment. But first, let's talk about driving this. Just like the vertical, the horizontal is comprised of two coils joined at one end. Now, why two coils? Why not one? Well, think about CRT. We're looking down the neck now, so we have a circular neck, electron beam going down the middle. To get nice symmetrical deflection, it works out nicely to have a coil on either side, and same for the other axes. So if you look at a yoke, it's sort of they're kind of flattened coils that are curved on the neck of the CRT. I'll pull one out in a moment and show you what it looks like. But that's why we have two coils. Now driving this, it's similar to the vertical, and if we really simplify this, in that it goes to a transformer. It goes to the secondary of a transformer. And that's the primary rather is driven by the horizontal output tube. In this case, it's a 6BG6. So, why do we have all this extra stuff? Why can't we just have a 6BG6 drive this? Secondary drives the yoke, and it would essentially be the same circuit as the vertical, using the 6K6, maybe just a little bit beefier. Well, as I said, that it's not so easy when that field collapses and you're going from one side of the screen back to start the next scan line. We need to do it very, 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 very quickly. When we do that, we have that extra energy. We need to do something with it. Some early designs, this definitely evolved. There were several stages of evolution. One of the earliest ways to do it was just burn it up. Put a big old power resistor or some such in there, and try to burn it off, absorb it, and then start the next scan line over again. Yeah, you can, but that becomes very, very power hungry. Or use a push-pull amp, just like an audio amplifier. And some sets did do that. If you watched my recent restoration of a Westinghouse set, that used a pair of 7A8 Lochtel beam power tubes and made a push-pull amp, and they drove a Yoke, and that's exactly how they did it. I also have a Dumont Clifton that uses a pair of 807 transmitter type tubes, and they drive it. So yeah, absolutely you can. Very power hungry circuit. So some very, 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 very clever engineers way back when came up with a rather brilliant innovation to do something with that energy. And that's where the damper tube comes into play. You could potentially just use a diode like with a relay or like a switch when you close it and you just shunt that collapsing magnetic field to, say, ground, and you just throw it away and then start over. You could do that. However, if you use a damper tube configured in a proper way, you can take that energy to drive the beam in the other direction. So think of it as a push-pull amp, but you've only got one half. Like the 6BG6 is driving one half, and the damper tube and its recovered energy is driving the other half. I did a video on this a while ago. I'm going to include it in the link, but I'll quickly summarize it here. It can be a little tricky to wrap your head around, so let's break it down. So here's our TV screen. If we have no deflection applied, if we just have high voltage and a focus circuit going on, the dot is going to be right in the middle. So that's why I used to think about how this would work, just naively thinking about it. I knew there was a sawtooth, and it was going to the grid of the 6BG6. So I'm thinking, okay, here's my sawtooth waveform, and it's going like this, and then it snaps back down. In other words, that when there's no power applied, that the beam would be on the left side, and that as this grid drive voltage, sawtooth going to 6BG6 builds up, it's pushing the electron beam across, and when it turns off, it snaps back to the other side and does the next line. That's not how it works. Because with no power applied, we're in the middle of the screen. How do you get on the left side if when the 6BG6 is conducting, it's going to drive the output and it's going to push it off to one side? How do you ever get to the other side? Well, if you had a push-pull amp, that's how your magnetic field would slosh back and forth. But we don't. We essentially have a single-ended amplifier. Now, you could shift the whole thing over with the bias circuit or capacitively couple it, I suppose, and it would do both sides, but that's not how this works. The way this works is this is biased as such that for a portion of this, the 6BG6 isn't turned on yet. This is very negative. This might be, say, negative 60 volts or something down here. The tube is completely cut off, and it doesn't start conducting till the center of the screen. So the 6BG6 actually starts conducting, turns on in the middle of the screen. And just this portion pushes it to the right. Okay? So we do have a sawtooth going to the grid of the 6BG6, but it's all biased and adjusted such that for half of it, the tube is not turned on. It's not doing anything. It only does for a portion of it. Then we get that cutoff. And the field collapses, and that energy is getting pushed back. So when the current is built up, we have current going through this. The tube is fully on. The magnetic field has built up. We turn the power off. That magnetic field in there has to go somewhere. Where it goes is it goes back into the circuit, but in the opposite polarity. That's where the damper tube comes in. The damper tube it's a diode, and it's a diode with the polarity set that it takes this energy and shunts it away. And like I said, we could just have a resistive load there, and the magnetic field collapses, and it goes through this diode, and it just goes away. Or we can do something with it. What we do with it is we get that quick snap of energy, and we use it to drive the yoke in the other way, the other direction. So when we get to the flyback, yeah, it instantaneously sort of, not instantaneously, but in a very short amount of time, gets us over here. And then as that magnetic field is decaying, it eventually gets back to here. So that recovered energy shoots us from this side of the screen back over here in a matter of a few microseconds. Then as that magnetic field decays and energy dissipates, we head back towards where we started from. So this portion, the left half, everything to the left side of the screen is damper. Damper, recovered energy dissipating. The right side is all horizontal output tube. So horizontal output tube conducting, recovered energy on the left side. That's really handy to know, because when you see issues on the set like ringing on the left-hand side, you know it's from the damper circuit. Ringing on the right-hand side or bad linearity on the right-hand side, horizontal output tube. And if you have a distortion in the middle, that means you don't have things set right. That's a real magic thing, is that the transition happening smoothly in the middle of the magnetic field completely collapsing from the damper and recovered energy to where the horizontal output tube starts conducting. That's where that drive setting comes into play. The drive setting on the set sets this operating point. It sets the amplitude of this sawtooth, and essentially it sets where that crossover point is going to happen on the screen. Crazy. It's crazy, but it works. It works because engineers put a ton of effort into this. So you might imagine, in order for this to work properly, everything needs to be matched. If you're unfortunate and encounter a bad yoke, a bad flyback, linearity coil, with coil, and you need to replace those, you may have trouble getting everything to look right on the screen with the screen geometry and whatnot. Because all of this stuff is tuned, you might say. Especially the flyback and yoke. Because the flyback drives the yoke directly. So that is the high-level overview of how this works. The actual specifics can vary quite a bit from TV to TV. I'll break down how this set does it, which is a pretty standard way of doing it because they basically cloned RCA. In fact, the flyback transformer used in this set is the same one that RCA used in their early sets, and a lot of others did. And the universal replacement for it is just called Fly 1. If you go to the Thord Arson or Merritt or other people that made replacement flybacks back in the day, this was Fly 1. This is the original flyback that worked with all these magnetically deflected sets, whether it's a 10 BP4, 12 LP4, etc. That's driven by a 6BG6. They almost all use this for a darn good reason. Somebody had worked out how all the component values and whatnot to make this work right, and if you were just launching into making a TV in 46, 47, 48, you best go with a proven design engineering. That's why I'm so intrigued and drawn to the guys who didn't, like Westinghouse, like Dumont. And it may not be so much that they thought that they could do it better, it's that they didn't want to pay royalties, I suspect, is a bigger reason. But Admiral, I think, wisely chose to essentially clone RCA circuit. So let's clear off the board and take a look at the actual circuit and then talk about how the high voltage factors in. Alright, let's see if I can draw a simplified version of flyback circuit here. This is our powdered iron flyback core. On one side we have the primary. We have a whole bunch of turns, tap, and a few more turns. This goes to our 6 BG6 horizontal output tube. On the other side, of course, we have a secondary. And that is driving our yoke. That tap in there. It's capacitively coupled on one side. And this goes over to here, and this is the part that always confuses me. Now this goes to B+. You would think this goes to B+, right? If this is your standard output transformer, you'd want to have a positive voltage here going to the plate to drive that. But no, you have B+ on this side. And what's all this about? We'll get to that in a sec. This works because we're about to add a damper tube into it. It gets everything going. So when your damper tube dies, you don't get high voltage because the damper tube completes the circuit. There's a different color for this. So this is very important. So let's go green for this. So our damper tube sits in here. And this is what goes over to here. So how can we get power to the primary side? B+ goes through the coil. When this tube heats up, it starts conducting this way. It goes around over there. So in this case, this is our 5E4. So that's the basic gist of it. Except for that. What's that for? I'll show you a simplified version of that. That is our high voltage, or EHT. You might be thinking, hey, don't they get the high voltage from the secondary, that big donut on there? No, that's actually part of the primary. It's an autoformer. Imagine if that wasn't there. Hey, this is just your standard output circuit, right? Imagine, ignore that. If we just had B+ there going to the plate of 6 BG6 and the secondary driving our coil, it's the same as the vertical output circuit. But they a way to do an easy, simple step-up transformer, rather than putting it on a secondary side, you can put it on the primary side. And just keep going with your primary and add more turns, and then rectify it. And that is how you get your high voltage. So that part's easy, actually. But this craziness, so no, we don't put B+ there. We put B+ on the secondary side, goes up through there, this tube conducts, and it comes back down around that way. And one little extra tidbit, there should be a cap from here to ground. That's a fun little thing there. So, because if you didn't do that, and we're driving this thing and it's oscillating, at this point, this would have AC component to it, and we don't want that. So why do they do that? Well, one of the reasons they do that is this voltage here is going to be higher than that. This is where you get your boost voltage from. So it's rectified, and then it's filtered by that cap, and this is actually your boost. That's your boosted voltage. That's what goes to the vertical circuit. That's why I wanted to take a break from working on other stuff to work on the horizontal, because I wanted to make sure this boost voltage was right, because without that being right, your vertical isn't going to work right. So that is the essence of it. There's one little extra clever bit in here. If you had a solid state rectifier, yeah, you could just do it like that. But we don't. We have a tube rectifier. So this actually goes to the 1B3. It has a 1.1 volt filament on it. We need to power that filament from something. And then this also goes off to our high voltage. There's no separate cathode in here. The cathode and the heater are one and the same, directly heated. Where are we going to get 1 volt to drive this filament that will have around 9 kilovolts riding on it? Simple. We throw a couple turns of wire around our flyback core. So if you ever see a flyback and it has a couple large turns of wire, or maybe just one turn around the core, that is just to power the filament of the 1B3. So very clever. So recap what we got going on here. We're driving the horizontal yoke. We're recovering energy with this clever damper circuit and getting it to fly back in a controlled manner. We're capturing that energy not just to deflect the yoke back on the left side of the screen. We're also filtering it and using it for the boost voltage for our vertical circuit. And we're taking an autoformer to make our high voltage. And we're powering the filament of the high voltage rectifier. That's why there's so much stuff going on the flyback. And there's a couple other little finer points in here too. So as I said, for all this to work correctly, everything has got to be copacetic. It's all got to be tuned. So they give you a couple means to do that. One is there's actually an extra little turn typically on here. And so this would be on the flyback, and then there are a couple taps, and there will be a variable inductor here. In this case, that's what the with control is. And then typically on this, there is a coil down in here. And there's actually another cap on this side. You got a little pi filter going on there. And this is variable, and that is your linearity coil. So adjusting the width and the linearity is done by tuning this circuit. And finally, the drive signal to this. There's a few ways to do this. I'll show you the simplest way. This is your horizontal drive. Variable potentiometer just simply varies the amplitude of that sawtooth wave going to the 6BG6. So as you can imagine, if any of these go out, if your linearity coil is bad, your width coil is bad, the yoke is bad, shorted turn and the flyback, messes up everything tremendously. And if you have to replace any of these components, it has to be perfectly matched or be close enough that you can correct for deficiencies by tweaking these adjustable coils. There's an interesting aspect to all this, and that is ringing. You may have seen or heard of a ring test on a coil or seen a ringer. This is a ringer yoke and flyback tester, a YF33, and there's a little symbol here of a decaying sine wave. That's a property of coils, that when you put energy into them and take it away, they ring as the energy dissipates. So, say you put a pulse into a coil, it decays away and you can count those rings. If the coil has shorts in it, you get fewer rings. Imagine you have like a tuning fork with a crack in it or something like that. It's not going to work properly. It doesn't resonate properly. Well, we've got that with this too. When we turn off the magnetic field and our yoke is collapsing, or the field in the yoke is collapsing, it wants to oscillate. The damper helps with that, but they actually take advantage of it. That's a very, very clever thing they do. So, as I said, we have that screen, and we have we've built up with that field, and we're at the right edge, and we need to get back over here pronto to start the next scan line. They take advantage of this. You kill that you cut the power off, you've got your sawtooth, and it comes down, and the tube turns off, and that field starts collapsing. It starts oscillating. They take advantage of that. They designed it so that they know what this decaying frequency is supposed to be. And, of course, it starts out with the biggest amplitude and then decays. The polarity is such that for the ringing for half of one cycle of this will get you over to here, and you won't see it on the screen. And then the damper by then has eliminated this when everything works right. When it doesn't, you see striations on the left-hand side because it's the resonation. It's still ringing a little bit. It's still resonating a little bit, but it's a tough thing to explain. But they actually want it to ring a little bit to get them back to the other side very quickly and then stop it. I'll try to point you guys to some reading material that explains that a little bit better. Now let's do a little show and tell. I happened to part out an Admiral chassis over the weekend. Yeah, sorry, we can't save them all. This is from maybe a year or two newer than the set we're working on. This is a yoke. So here's one set of windings, either the pair vertical or horizontal, and the other is beneath it, behind it. I can take off this cover on one end. Let's see, there's some bits inside. Those are the resistors for the vertical to control ringing. And then there's a compensation cap across one of the horizontal windings. It's very typical. And we have 4 wires coming out. 2 horizontal, 2 vertical. So that is our yoke. And here is our flyback, or a flyback. Very similar to the one in our set. You see there's a number of stacked up coils in there. This outermost one, with this wax coating on it, that is that autoformer winding to make the high voltage. So this wire coming out here, that will be your 10,000 volts or so. And then stacked within it we have several layers of other coils. And this thick wire, we just have a couple loops here, that is the filament winding for the high voltage rectifier. So the tube would go in there, and this is the actual rectified high voltage that goes to the CRT. This typical flyback construction where it's powdered iron core and a couple pieces. The coils are fit on there, and then there's a phenolic board with all the various taps going to it so you can hook up your width and linearity and your yoke and all that stuff. Now back to our chassis. I did do some basic recapping down here in the horizontal circuit. So horizontal output tube, damper tube, I replaced about 5 paper caps down in here and 1 resistor that was a bit off, and that's all the work I did. That is the drive control. This is the coil that sets the free running horizontal frequency. Let's wrap up this video by taking a look at what kind of image this set actually produces with some video content for the first time. We've been looking at test patterns all this time. I thought, hey, let's actually feed a video signal in. And it's not bad. But a few things jump out at me right away. One, it shifted over too far to the left. You can tweak the horizontal framing a bit with the horizontal hole control, but that's not how you're supposed to do it. There is a mechanical adjustment on the neck to shift the image left, right, up, down. So we'll get to that. But the image quality, it looks pretty sharp, but the contrast, it's sort of white and black and not a lot of good gray level in between. The contrast control works kind of oddly on this, so I just went full counterclockwise, and the picture just disappeared. Now I'm going clockwise with the contrast. Starts coming in, looking pretty all right, but it's even so, it's too, like his whole face is just white. You can't see any detail. If I keep going, It's getting a little better, kind of, but it's also getting dimmer. And if I keep going, now it's almost getting like inverted, or it's not inverted, but it's clearly gone too far now. I'm fully clockwise with the contrast, so back it off a little. It doesn't seem to be a good point. I'm kind of maybe there. Or turn the brightness down a little. You can play around with it. You can get it looking pretty good, but I don't think it should be quite so finicky. But we haven't done any work yet on the AGC contrast video amp stuff. See, like his shirt, you can't really distinguish it from the sky. It's just all white. I don't think it should be quite that harsh. But hey, this is a great place to be in this project. It should only get better from here. And might as well check it out, a little Star Trek action. These weird kind of lines in it too, which I think are chroma dots. So, oops, I'm control and turn this off. That's something that's hey, there's a dot. That's an interesting artifact. We'll talk more about it a bit later, about when you come to feeding a signal into this set. This set was designed pre-color. And it has a full bandwidth, has excellent bandwidth. So when you put in a later color signal, you see the color info show up as weird dot patterns in the black and white image. We don't want that, but it also means that we have a great TV because this has really good bandwidth. So if we can somehow generate a black and white signal, no color info, that has the full 4.5 megahertz bandwidth, we should get an outstanding image on this screen. There is one other little quirky thing. Let's see if the camera can pick it up. This may surprise some of you. Oh yeah, you see those little specks? Try to wipe them off. You know what those are? Those are bubbles in the glass. That's pretty common on early CRTs. Hey, it's picking it up real well. Think of that as dead pixels in a modern term parlay. That was acceptable back then. That was, I've seen worse than that. But yeah, all these little specks of light, those are little bubbles in the glass. The largest one in the middle, it's kind of visible once you know it's there when you're watching video. It's part of the charm, I guess.